All right, so this is our second problem, and you see, compared to the one we just did, there's something a little different here. We've got a continuous load. In this case, it's a uniform load. So just like we did before, the problem says, hey, I want to find what's happening at point C, and I've already indicated that, but I'll go ahead and draw a line through there, make it easier for you to see. So now we want to know, do I want to work the left side or the right side? There's really not much difference between the two. If you look at it, both sides are going to require a reaction of some kind. And both sides, it's a uniform load on the left side, it's a uniform load on the right side. So really either one will work just fine. I'm just going to go left. Why not? So I'm going to assume, not assume is the wrong word, I'm going to draw a free body diagram of my beam. And I'm going to do something a little different than we've done before. No, I won't do that. Never mind. I'll save that for later. I'll hold on to that surprise for later. So I'm just going to say I have a reaction AY here, a reaction BY there. And to manage the uniform load, I'm going to replace it with a concentrated load that is equivalent. And all I need to know is the area under the curve. What's a rectangle? So this is going to be base times height. That's 18 times 3. Is that 54? Yeah. So there's my equivalent load, which will be 54 kips, and it'll be in the center of this value. The centroid of the rectangle is in the center, so half of 18 would be 9. Now, since I'm going to the left, I only am really interested in AY. So when I sum moments for this particular problem, I'm going to sum them at B. Summing moments at B, I can find AY in one equation. So I'll do that. So about B, with my right-hand rule sign convention, the 54 kip force creates positive moment. So I have a positive moment of 54 kips times 9 feet. And then my reaction at A is negative moment. So that'll be unknown AY, and that is a distance of 18 feet. So it looks like AY is going to be equal to 27. Does that sound right?
Are you trying to say the fact that since they're at equal distances, the forces in the one is equal?
Well, usually in a beam like this, a simple supported beam with a uniform load, basically half the load is on one side and half is on the other side. But we didn't have to think about it. The equation says that. But it does make sense that half would go. So I'm going to make this slightly larger just to give myself a little more room. So I'm going to draw a little bit bigger free body diagram of this section to the left. So I know it's 6 feet. I now know my reaction at AY is up, and it's equal to 27 kips. And I've got this distributed load, which is acting down, but I'm going to replace it with a concentrated equivalent. So this section of the load, it's still 3 kips per foot for the intensity or the height, but the distance is only 6. So 6 times 3 will give me 18. And half the distance should be 3 feet from either end. And then at the cut surface, I'll draw my positive axial force, positive shear force, and positive bending moment. And I'll just subscript those C because we're doing it at point C. That's it. So if you're doing this problem on the exam, you just got half the credit. So now you break out your 3 equations of equilibrium and you plow away. So it's always a good idea, usually, to start with summing moments at the cut Why is that? Well, my axial force and my shear force are concurrent at the cut point, so I don't have to worry about those. So looking at the moment about the cut, my assumed my positive bending moment with this sign convention creates a positive moment. Now my equivalent force of 18 kips about the cut, is that positive or negative moment? Positive. So that's a force of 18 kips, and the distance from the cut to the line of action is 3 feet. And then my reaction force about the cut, that 27 is creating negative. So it'll have a value of 27 and a moment arm of 6. So let's solve for the moment at C. It looks like it's going to be positive. I don't know what the value is going to be. What is the value? 1 gajillion. 108? Exactly?
Yes.
Oh, cool. 108. 108, that's a magic number. Pretty cool, huh? It came out positive. Does that make sense? Yeah, if we go back up and look at this beam, how do you think it's going to bend? You think it's going to bend up? No, it's probably going to bend like that. And if you look at that, it's a happy face. Positive moment probably pretty much throughout the beam. So it matches the positive value there. So let's finish the calculation. So I now need to sum forces in the y direction. Make sure that's in equilibrium. That should tell me what my shear is. So I'm assuming up is positive, so this shear force is down, so that's minus. This equivalent force of 18 is down, so that's minus. And my reaction force is 27, that's up, that's positive. So the shear at C is equal to positive and probably equal to 9. Did you get your calculator out for that one? 9. Very good. Cool. Oh, I guess I should do the last one. Really not much going on there. But if you did sum forces in the x direction and put it in equilibrium, what do you get? You just get the axial force at C, so it has to be true.
If we didn't write that, would you say that's points?
Only if I asked you for it. You notice the problem just says, what's the internal shear and moment? It doesn't ask for axial force. If I said axial force and you failed to account for that, that could be tricky. Any questions about that? Should we work the other side of the problem just to show you that no matter what side you pick, you get the same result?
No.
No? You believe me? Excellent. I've got some great land I can sell you in North Carolina, just downriver of a hog farm. Choice.